Next, we will examine merge sort and how it works. If the data can be partitioned into smaller chunks, it can be obviously easier to sort the list. And that's the idea behind merge sort. It was first developed by John von Neumann back in the 1940s. And this is a divide and conquer algorithm. The idea is if I can take an array or a list of some sort and I can divide it all the way until I only have a single element, well, then that single element is sorted, and all I have to do is be careful when I assemble that element with other single elements that make up my array. And hopefully that will make sense again when we go over some examples. So as a divide and conquer algorithm, the divide part is the actual splitting of the array. The conquer part is the actual work that gets done, and it turns out that the work in this case is done by the merge function, which we will consider in some detail. And that's what gives us the behavior of this algorithm. So this will be an n log n algorithm again, and the fact that we're subdividing the array in half each time gives us the log n behavior, and the fact that at each level I have to deal with each of the items in the array, all n items in the array, that gives us our n behavior. So for each item in the array, n, I potentially have to do log n amount of work to have this come out sorted on the other end. You see the pseudocode there. Again, it is just a compact piece of code. It is a recursive function. So you notice that merge sort, this is the function header, and as long as the indices are some space apart, first being less than last, we calculate a midpoint. We sort, we call merge sort with the left half, so going from first all the way to mid, and then we call merge sort on the second half from mid plus 1 all the way to last. And then those are just divisions once again, and then merge actually merges the data for the entire instance of the function. So let's take a look at a little bit more detail. The divide step, as I mentioned, is fairly straightforward. Calculate the midpoint of the array and call merge sort recursively on both halves. The left half gets done first and then the right half. The conquer step is performed by the merge function. So here's a description of the merge function. On return from recursive calls, both halves of the array, both halves that I'm dealing with at that level, the subsequence or the subarray or the sublist, both of those halves are individually sorted, but they're not sorted as one whole. And so the idea is to build a single sorted sequence from two subsequences that are already sorted. And the steps to undertake is first to allocate space for the combined sorted sequence. This clues us in that merge sort is not an in-place algorithm. It turns out that it requires 2n space. So if I have n items, I require double the amount of space in order to be able to do the work that's required by this algorithm. But getting back into this, we'll allocate the space, and then we'll take a look at the first element of each sorted half, and we will take the smaller element. This is for an ascending sort. We will take the smaller element and copy that into our final container, and we will remove that element from its appropriate list. Okay, and that's step 3. If at any time one of the halves is empty, we simply copy all remaining elements from the non-empty half in order to the final sorted container, removing each from that list, from the remaining list. And then we repeat steps 2 through 4 until both halves are empty. So let's look at a concrete example. Let's say that we've been executing merge sort, and I'll take you through a more complete example from beginning to the end. But I want to convey what the merge function does so that you have that context when we look at that end-to-end example. So let's just, regardless of whether this is merge sort, let's just take a look at what it would take to merge two halves that are individually sorted into a single sorted sequence. So here are the steps. First of all, we want to allocate space for the final sequence. In this case, I've got a list of 4 items and a list of 3 items, so I need n equals 7, so I allocate my array with 7 elements. I then want to compare the fronts of the list, and that's what I mean there is take a look at the first element in each list and pick the minimum. As I look at the 2 and 3, I'm going to take the 2 because it's the minimum of 2 and 3. I'm going to add it to the final array, and I'm going to remove the 2 from the list. Okay, so it looks like that. My list now is made up of the list 7, 10, 12 and the list 3, 6, 9. And I repeat this whole process. I take a look at the fronts of the list. Okay, and I'm going to take the 3 because it's the minimum of the 3 and the 7. I'm going to add it to the final container and remove 3 from the list, and that looks like this. I continue with the next step, which is to take a look at the 2 front elements of the list again. It's the 6 and the 7 in this case. I'm going to take the 6 because it's the minimum of the 2. I'm going to add it to the final container and remove it from the list. I now look at the 7 and the 9. The 9 is the only element in the list, but it is the front of the right list, the right half. Look at that with the 7. I'm going to take the 7 because it's the minimum of 7 and 9, and I will add that to the container and remove the 7 from the list. Okay? And now I will look at the 9 and the 10, and I want to repeat this process. I will take the 9 because it's the minimum out of 10 and 9, and I will add it to the final sorted container and remove it from the list. You now notice that the right half is empty, okay? So as the algorithm steps in the previous slide mentioned, if the right half is if the right half is, if any half is empty, then we just want to go ahead and copy the remainder of the non-empty list in order. So we'll copy the 10, removing that from the list, and we'll copy the 12, removing that from the list. In this case, the lists are both empty, and if you look at our final container, it is in fact sorted in ascending order. Okay, now here is an example sort of from end to end. The idea is that we're starting with this unsorted sequence at the top, and we're going to go through various function calls, recursive function calls, and merging using the merge function to get to this final sequence that's at the bottom, which is in fact sorted in ascending order. So let's do a step by step. So I've copied the algorithm pseudocode down so we can refer to it. I've placed a line on this diagram, and I will tell you what that means in a second. So the number of data items here is 9, and the unsorted array is at the top, as I pointed out. That you will see a blue underline that will show up under various instances of the array. That is the index mid, which is calculated from the first index plus the last index, integer division by 2. You will see some numbers that will show each step that this algorithm takes. There will be a total of 24 steps, and 0 is the first step, and it signifies a call to this function on the upper left from some external entity like main or another function of some sort. If we see m followed by a value, that is the merging of the results from the ith step. And again, I will point that out as I explain the behavior of the algorithm. Recursive calls, which is a deepening of the recursion, take place above the line, and below the red line is the unwinding of the recursion as the various base cases are reached, or as the function actually terminates. So the base case in this case is the bottoming out that happens when first is not less than last. So it's an implicit, it's not explicitly stated, but the base case is, if you look at this function, if this is not true, then that is the base case, because the function does not call itself. Okay, it simply terminates and returns to the previous instance. So finally, we'll end up with the sorted array at the bottom. So let's look at the sequence of events. This is the 0th call, so merge sort is called and this array is passed. First is 0 and last is 9. And so we're going to calculate mid, okay, which is at index 4, as you see there. And so that's this line of code, and we're going to call merge sort on everything up through mid. So from first all the way through mid, and this is the first recursive call. So this function has now been called with just the smaller list, and it's as I say often with recursion, it's a brand new day. And so we enter that instance of the function for the first time. First is less than last, so we calculate a mid. Okay, it's right there. And we call merge sort on the left side of that list, going all the way up to mid. So the 1, the 8, and the 6, and we end up at this point, right? So as you can see, the recursion is deepening here. I had the initial call, which was non-recursive call, but I've had 2 recursive calls on the left side of the array only, okay? So we take a look at the 2, at that second, at step 2, and let's calculate that particular midpoint, and we call the function recursively up to that point. So we call it with the 1 and the 8, and that's step 3. Let's calculate that midpoint. It's here, and we call this particular function. Now, when we call the function recursively here, it only has one item. So first is not less than last. That means that instance of the function terminates. So this always happens when you're down to one element. In this case, 1 by itself is sorted. So this instance of the function terminates and it returns to the instance at step 3. Well, what has that function done? Well, it had calculated mid and it had called merge sort on the left side. It's now going to call merge sort on the right side. And it does so. And the same situation takes place here. We're down to only one element, so first and last are not less than, first is not less than last. They're in fact equal to. So that instance of the function terminates and it returns back to the function at step 3. And what have we done? Well, we've gone to the left, this one, we've gone to the right, this one. We must now merge these two lists. When I merge the 1 and the 8, with the example I showed before, I simply put the 1 in front of the 8. So step 6 here is a merging of the results from step 3. Okay, so it's important to realize that this merge did not come from 4 and 5. It came from step 3. 4 returned to 3, 5 returned to 3, and then that was the left call. This is the right call. So now this is the merge call in step 3. Okay, and once we do the merge call, the function ends. There are no more statements beyond this. There are no more recursive statements. So the function unwinds. I was at 3. Okay, so I unwind back to this location, to step 2, the instance of the function. Well, what have I done there? I calculated mid and I went to the left, so I now go right. And it turns out that there's only one element there. And so first is not less than last. It's actually equal to. So the recursion unwinds back to the function call at step 2, the function instance at step 2. And I ask myself, what have I done? Well, I've calculated mid, I've gone left, and I've gone right. I must now execute merge on the instance at step 2, which happens here. And you notice that I'm merging the list 1, 8, and the list 6, giving me the list 1, 6, 8. Again, assembled by the merge function as we saw previously. At this point, once I hit the merge line, the function terminates and unwinds. Well, where does it unwind to? Well, we've just executed the merge line for this, so it unwinds back to this point. What have I done? The instance of the function is step 1. Well, I calculated mid and I went to the left. So now I must call merge sort on the right half, and I do so. And here we are at step 9, and I still have a 2-element list, so I calculate a midpoint. There it is, and I call it on the left half. Okay, and that's a 1-element list, so the function unwinds. Right, that instance terminates, unwinds, goes back to 9. What have I done at 9? Calculated mid, called merge on the left. I now call merge sort. I called merge sort on the left. I now call merge sort on the right. That's a single element list. So that terminates, goes back to 9. What have I done at 9? Well, I've calculated mid. I've called merge sort on the left half, called merge sort on the right half. I will now merge those two results. So I merge the 4 and the 10 in step 12. And this instance of the function terminates because merge is the last line. It doesn't have a recursive call in it. And it unwinds. Well, where does it unwind? Well, it was back here at 9, right? Where I went left, I went right, then I merged. So I unwind back to this point. What have I done here? I've done everything. I've calculated the index. I've called merge sort on the left, called merge sort on the right. I now have to perform the merge for these two. Okay, so here it is. I now, at step 13, I merge the lists that resulted from the instance of the function at step 1. Okay, once that instance is done, I unwind all the way back to the top. This function is terminated and I go back to the 0 call. What have I done? I calculated the index at 0. I called merge sort on the left half. I must now call merge sort on the right half. And I do so. And brand new day, I enter this with these values. I have to calculate an index, midpoint, and I do so. And I call the merge sort function recursively on the left hand side, and that takes me here. And I first is still less than last, so I calculate a midpoint and I call it with the left hand list, and that is the 5. Okay, and a list by itself, the function terminates, unwinds back to 15 here. What have I done at 15? I've calculated the index and I've called merge sort on the left. I will now call merge sort on the right. And that is a single element list. So that instance of the function terminates and it comes back. What have I done? Calculated the index, called merge sort on the left, call merge sort on the right. That's these two lines. I now have to merge the data. Okay, and I do so. And I merge the calls at the instance of the function that's at step 15. And since the merge is the last line, it unwinds back to, so it's the last line of 15, so it unwinds back to 14. What have I done at 14? I calculated the index and I call merge sort on the left, so I must now call merge sort on the right, and I do so. Okay, that's a two element list, so first is less than last, so I calculate a new index and I call merge sort on the left hand side. That's the 2 by itself, and the function terminates because first is not less than last, it's equal to last, unwinds back to the 19. What have I done at the 19? I've calculated the index and I've called merge sort on the left. I will now call merge sort on the right, and that's a single element list, and the function terminates. I unwind back to 19. What have I done? Calculated the index, call merge sort on the left, call merge sort on the right. I must now execute the merge function where I merge call 19. So in step 22, I merge the calls that were in 19, and then I unwind back to 14. And what have I done at 14? Well, I calculated the index, call merge sort on the left, call merge sort on the right. I must now execute this for the function instance at step 14, which is to merge that list. And so the list 3, 5, and then 2 and 22 get merged into 2, 3, 5, and 22 as shown previously. And the recursion unwinds back to 14. I'm sorry, the recursion, the instance merge terminates. The recursion unwinds back to call 0. What have I done at call 0? Well, I have calculated an index. I've called merge sort on the left. I've called merge sort on the right. I must now merge the items, which I do here by merging the calls at 0. The function terminates at that point. There is no more unwinding to go through, and I'm out of the function, and the data is sorted as you can see at the bottom. So some things to consider when implementing merge sort. Merge sort lends itself to sorting linked lists. As a matter of fact, if your data is in list form, merge sort is usually what is used. Because we don't require random access to the individual elements, we only compare the first one, so the merging is fairly straightforward. But breaking up the list into 2 equal halves presents some difficulty. And so usually this is a linked list that ends up maintaining a count of how many nodes it holds. And then as we go through the process, then we can just count 1/2 of that and put that in the left list, and the rest of it is in the right list, and we can continue from there. As far as arrays go, splitting into 2 subarrays is easy because we just do that by the indices. That was the example that we just followed. And merging is also easy. We just need a second array to do that, as I showed you when we looked at the merge function a couple of slides ago. And so there are a couple of ways to merge into this auxiliary array. To avoid having merge operations actually each declare a new array, what we can do is set up 2 arrays to begin with, and then just rename them as we go through, rather than having to copy everything out of aux, the auxiliary array. we'll just say that that auxiliary array is now our main array, and we'll make our main array, we'll just clear it out and make that the auxiliary array. And that makes this a little bit more efficient, especially when you have a lot of data or the size of the data is large. So here is an implementation of merge sort. What I showed you before is basically pseudocode, but as you can tell here, this is from a different textbook. It's pretty much what we just described. This one has the code for the merge operation with it. It does not consider merge a second function. And so all of that information, as we mentioned, the possibility of lists being emptied, that's handled there. And otherwise, the comparisons and the copies get done by these other two lines based on which one is the lesser item.